This is the concluding lecture on the topic of rupture of thin films. In the previous lectures, we have derived the evolution equation for the thin film equation. The height of the thin film is given by this partial differential equation involving time derivatives of height, which is related to the pressure gradient in the thin film. The pressure term involves the atmospheric pressure above the thin film, the hydrostatic pressure because of gravity. Then we have curvature terms, which is because of surface tension. And finally, in the previous lecture, we discussed the role of a new term which can contribute to rupture of the thin film, which is the disjoining pressure. This disjoining pressure is from the intermolecular force named as the Wonderwall Force. What we'll be doing in this lecture is to write down the evolution equation for the thin film again, and we will be simplifying this equation by defining a few important parameters, and we'll then be carrying out a linear stability analysis of this equation to understand how which wavelengths grow and which wavelengths decay. So that will be the dispersion relation for this thin film problem. So let us begin by looking at the evolution equation for the thin film. The evolution equation of the thin film has already been derived in the previous lecture. I'll start with these two equations here. The first is basically the relationship between height and the pressure gradient, the horizontal pressure gradient. And the pressure itself has four parts to it. We will eliminate the horizontal length scale L because it is arbitrary, and we'll define everything in terms of the vertical length scale H0. So for example, this term pressure P0 will become, we have to remember that epsilon for us is H0 by L, which is much smaller than 1. So wherever there's L, I'll replace it with H0 by epsilon. So essentially what we get now is epsilon H0 square rho G by mu U0 times H minus Y. Then we have epsilon cube by capillary times HXX. And finally we have the van der Waals term, which is A epsilon by 6 by mu U0 H0 square by 1 by H cube. So let us define the following parameters. These parameters will help us to write this equation in a simpler compact form. We'll define a parameter, a gravity parameter, which is epsilon times G, where this G is rho G H0 square by mu U0 gravity parameter. We'll define another parameter C bar, capillary by epsilon cube. Remember, Ca is mu U0 by gamma. That's the capillary number. And finally we have a parameter A bar, which is nothing but the non-dimensional Hamaker constant. So everything in the brackets essentially goes into this. So this is non-dimensional So the compact form of the pressure now simply becomes P infinity minus G bar of Y minus H minus 1 by C bar of HXX plus A bar by H cube. This is basically my pressure. And now I can calculate the pressure gradient, del P by del X. This will simply be G bar of minus Hx then we have the derivative of the curvature, and finally we have the last term Hx. Now I can substitute this into my thin film equation. Remember, the thin film equation is del by del H. Del H by del T is del by del X of H cube by 3 del P0 by del X, and this is H cube by 3 times del P del X, which we've already derived just now, G bar Hx 1 by C bar Hxx minus 3A bar by H bar 4 Hx. So let's multiply H cube by 3 with the terms there. So we have, I'll do 2 steps at one shot. I will multiply and then take the derivative simultaneously. And we have G bar H cube by 3 Hxx and finally the 2 terms from the Wonderwall Force. This is all the terms that we have here, and if we now substitute this, we can do a few simple cancellations here. For example, the 3 cancels with this 3 here, and what do I now have is G bar H cube by 3 Hxx Hx square fourth derivative of H. Then we have so that completes the evolution equation for the thin film, including the Wonderwall force. Now this equation is a non-linear partial differential equation. Okay. Now notice that there are several derivatives that appear. There are fourth derivative of H. Then we have product of H with H in the, for example, all the terms in this equation are basically nonlinear. Okay. So what we can now do is to recognize that we have a thin film here. The original unperturbed thin film is, let's say, we have defined the original unperturbed thin film to have a height of h0. On this unperturbed film, we have created a perturbation to the thin film, some arbitrary perturbation. Now the arbitrary perturbation can be defined as follows. We can say the dimensional height y will be the dimensional h naught plus in eta tilde, and this is nothing but h of x comma t, all in dimensional form, right? So in other words, we are saying that h tilde dimensional is equal to h naught plus eta tilde. Remember, h naught is the height and it's a dimensional quantity, and therefore the non-dimensional height, which is h tilde by h naught, would simply be 1 plus eta, where eta is defined as eta tilde by h naught. This is the non-dimensional deviation, right? So in other words, this quantity here that I'm showing here, this is eta tilde. This is the deviation of the interface from flat surface. Okay. We will also say that the magnitude of this eta is much smaller than 1. So in other words, 1 plus eta is approximately 1, okay, but with a small term. So therefore I can say del h by del t therefore essentially becomes del eta by del t, del h by del x essentially becomes del eta by del x. And if we basically take an example like a term like h cube times hxx, this is basically the first nonlinear term that we have. This term essentially would become 1 plus eta whole cube times hxx. What is hxx here? It will be eta xx. Remember, the subscript x essentially denotes a derivative with respect to x. Now I can do an expansion here. This would be 1 plus eta cube plus 3 eta square plus 3 eta times eta xx. So this is nothing but eta xx plus small terms. Why are they small? They're small. This is because these are non-linear in eta. All terms non-linear eta is small because of this condition that eta square magnitude of eta is small. That's the perturbation, the deviation of the interface from the undisturbed state is very small. Therefore, we'll only retain the linear terms. So just for completeness, I'll write down the evolution equation. So we have the evolution equation after substituting h is equal to 1 plus eta now becomes del eta by del t will be g bar by 3 1 plus eta whole cube times eta xx. We have g bar times 1 plus eta whole square times eta x whole square minus 1 plus eta whole cube by 3 c bar fourth derivative of eta that's the other term. Then we have the first van der Waals term, and finally we have the last van der Waals term, which is 1 plus eta whole square into eta x square. Now I'll underline several terms which are very small in eta. So for example, this term, the second term, is nonlinear. the fourth term is nonlinear, and the sixth term is nonlinear. All these are nonlinear in eta, and hence these are small. These are small. So if I ignore these nonlinear terms in eta, what I now have is a simplified equation, a linear equation, which is approximately g bar by 3, only the linear terms, eta xx minus 1 bar by 3c, eta xxxx, and finally I have minus a bar eta xx. So this equation is a linear partial differential equation. So what we have done is we've gone from a non-linear partial differential equation now to a linear partial differential equation. A linear partial differential equation of this kind with constant coefficients, I can always straight away assume a variable separable form. So in other words, if you notice here that this is an interface which is basically going from minus infinity to plus infinity in the horizontal direction, and any arbitrary interface like this, any arbitrary disturbance of this nature, which is eta hat, can always be written in terms of, we can do a Fourier decomposition in the x direction. We've already done this for when we discussed the when I gave you a brief introduction to linear stability analysis. So we'll be following that discussion here as well. So the idea is the following. So we have eta hat of x and t. We'll assume it to be some beta hat, some amplitude times e power I k hat x hat minus omega hat t hat. Okay. Now we can define the horizontal length scale in a more precise way. If this is my length scale, then my k hat is basically, you can think of it as 1 by wavelength, and that can be taken to be the characteristic length scale. The characteristic length scale is the wavelength itself can be taken as the length scale, and therefore I have x. Remember the non-dimensional x was x by L, and therefore I have k hat of x hat, k tilde x tilde, which is the product of the dimensional wave number multiplied by the dimensional length, essentially becomes 1 by L times xl. That is nothing but simply x. This is the non-dimensional x. Okay. Similarly, we can define a non-dimensional complex frequency as omega tilde multiplied by L by u naught. Okay. And since we have the non-dimensional time t tilde to be L by u naught, we simply have omega tilde t tilde will become S by L by u naught multiplied by t into L by u naught, and this simply becomes St. So what we have now is, and we also know that eta hat essentially becomes eta times h naught, and the amplitude eta is basically the deviation of the interface from the undisturbed state, and beta hat is the amplitude, the dimensional amplitude of this interface from the flat interface, and beta hat simply is nothing but beta times h naught. So my equation essentially becomes the amplitude equation instead of eta tilde. So I'm referring to this equation here. Eta tilde essentially becomes eta Ix plus St. This is the way I've defined my equation. Now notice that if real part of S is greater than 0, then we have unstable state. If the real part of S is less than 0, it is stable, and that if the real part of S is equal to 0, then we have a neutral stability, right? So let's just simply substitute this. So for example, eta x simply becomes I beta e power ix plus st. Similarly, eta xx becomes I square beta e power ix plus st. This is nothing but minus beta e power ix plus st, and so on. If we substitute all these derivatives of eta, including the time derivative on the left hand side, into the linear PDE, then what we get is a simple algebraic relationship. Eta into the linear PDE that we have derived we will get S is equal to G bar by 3 I square minus 1 by 3 C bar I to the 4 minus A minus A bar of I square. The exponential terms on both sides get cancelled out because they can never be 0, and therefore I have a simple relationship. S essentially becomes A bar minus G bar by 3 minus 1 by 3 C bar. This is my dispersion relation. Okay. This is a very important result that we've got. We've basically got the growth rate S in terms of the parameters A bar, which is the Hamaker constant, G bar, which represents gravity, and C bar, which represents the capillary number or the inverse of the capillary number. Okay. We look at a few special cases. We look at a few obvious ones. Let's start with some simple special cases. The first special case that I'll consider is A bar is C bar inverse is 0. So A bar is 0, which means that there is no Wonderwall force. If I say 1 by C bar is 0, it means that there is no surface tension force. So this is no surface tension, no Wonderwall force. Okay. Only gravity present. Okay. So what do we get for S? S simply becomes, if I look at this equation, we'll label this equation as equation star. Equation star essentially reduces to S becomes minus G bar by 3. Okay. Right? So clearly S is less than 0 if G bar is greater than 0, which means that if gravity term is positive, this term is positive, then S is always less than 0. It means that the undulations die out with time, and this is a stable flow. Okay, it's stable because we have undulation, this gravity will try to reduce it, and finally the presence of viscosity will dampen out all oscillations, and what we have is a stable flow. There is no oscillations at all in this particular problem. It will just return to its stable state and stay there. Okay. Now let's look at another special case, which is A bar is G bar is 0. That is no gravity, no van der Waals force. Right? Again, in this case, S essentially becomes, if you look at this equation, the first two terms in the bracket disappear in the equation star. We have minus 1 by 3C bar. Okay, which is always less than 0, since C bar is always greater than 0. Right? So again, if you recall, C bar was defined as epsilon cube by capillary number, and that's always a positive quantity. Okay, so again, we can conclude that surface tension is stabilizing. Okay, in this particular problem, surface tension is a stabilizing force. Okay, let's consider a few other cases. For example, if gravity term is equal to 0, which means that it's a thin film, so such a thin film that gravity may not be very important, then we have S will be A bar minus 1 by 3C bar. So we can conclude that the film is unstable if S is greater than 0, and this would happen when A bar is greater than 1 by 3C bar. Right? So let's, to get an understanding of what this means, we'll substitute the expressions for A bar and C bar. So this essentially translates to A epsilon by 6 pi mu u naught h naught cube is E greater than epsilon cube gamma by 3 mu u naught. Right? This is basically my expression for so this is a small correction here. This should be h naught square. Okay. So what do I now have is, we can do a few simplifications. For example, this mu u naught on both sides cancels out. So viscosity straight away drops out. Meaning viscosity does not determine the stability boundary. And we can now further simplify this to say A by 2 pi h naught square is greater than epsilon square of gamma. Or in other words, A by 2 pi h naught square is greater than epsilon square, remember, was nothing but h0 square by L square, but we've taken L to be the wavelength of the instability itself, that is lambda square gamma. So this is only valid when wavelength is large compared to the thickness of the thin film. Sometimes this is also referred to as a long wavelength analysis. That's what we have done. And now we basically have lambda square will be greater than, if lambda square is greater than 2 pi h0 power 4 gamma by A, we have an unstable film. Okay, let's verify that the units are correct. The units of right hand side would be meter per 4. Gamma will be Newton per meter square. Newton per meter, sorry. And Hamaker constant is Joule. And Joule is nothing but Newton meter. Right? So the Newton cancels out and meter square becomes meter. So essentially right hand side is also meter square. Okay, the units are all right. So now what we have is if the wavelength of the disturbance exceeds a value of 2 pi h0 power 4 gamma by A, then it will grow exponentially, right? So long waves will become unstable because surface, as the wave becomes longer and longer, surface tension basically becomes weaker and weaker, because remember, surface tension acts at a small scale, but as the wave becomes longer and longer, surface tension becomes weaker and weaker. We can also ask what is the typical thickness that we need for van der Waals forces to become important. We will do this calculation not for a special case but for the most general case. Here we have assumed that gravity is not important. We will also put in the gravity term and then we will see what's the typical thickness of the thin film when this becomes, the van der Waals forces become important. Okay. We'll look at another special case. This is case number 4. If surface tension term is 0, that is 1 by C term is 0, then we have the growth rate, non-dimensional growth rate is S is equal to A bar minus G bar by 3, and we have unstable if A bar is greater than G bar by 3. I will leave it to you to substitute the expressions for A bar and G bar and determine what's the relationship between the wavelength and the gravity terms. Okay, just like we have derived here a simple stability criteria. The stability criteria that we defined for the previous cases, lambda has to be greater than, the wavelength has to be greater than above a critical value for this to be unstable. So short waves, if the wavelength is shorter than a certain value, and how do we, if the wavelength is shorter than a certain value, then automatically you would expect stabilization to happen because this inequality will not be satisfied. Okay. Now, we should also consider another simpler case. These are all these cases are special cases where we are basically ignoring typically one force. We will finally consider the special case where if A bar is 0, then we have C bar. Okay. Now this essentially will reduce to 1 by 3 minus G bar by 1 by 3 C bar. Right? Now, if G bar is greater than 0, then we can immediately say, remember the capillary parameter, that is C bar, is always positive. Okay. But the value of G bar can be positive and negative depending on the sign of gravity or the direction of the gravity vector. Okay. If G bar is positive, S is less than 0 for all wavelengths. This is linearly stable, right? But if on the other hand, if G bar is less than 0, what is G bar less than 0? So the gravity vector is in the opposite direction. So remember, our original problem was like this. The schematic that we had taken was a thin film with gravity downwards. This was liquid and gas. But if the gravity vector is in the opposite direction, which means that I will have to change the direction of the gravity, this is equivalent to saying that I have a thin film like this. We have a solid substrate and I have a thin film which is with gas below it and a liquid above it. And the gravity vector is now pointing from liquid to gas. Okay. We know this is an unstable configuration intuitively because heavy over a light fluid would be unstable. Well, not always. It's unstable provided the gravitational forces are able to overcome surface tension forces. What does this mean in terms of dispersion relation? If G bar is less than 0, then we have S becomes 1 by 3 magnitude of G bar minus 1 by C bar, right? And therefore it is unstable if the magnitude of G exceeds 1 by C bar, or in terms of parameters, if we substitute the expressions for G and C, we have rho G H naught square by mu U naught is greater than epsilon cube by capillary number. And what does this mean? This means that in terms of the dispersion relation, if we substitute the expressions for if we do some cancellations here, if we substitute the expression for capillary number, what we end up getting is a simple relationship. Rho H naught square G is greater than H naught square K square times gamma, right? And here I basically used the expression for epsilon as H naught by lambda or H naught times K. That's the expression for epsilon that has been used. And what we now have is, if K square is less than a quantity which is rho G by gamma, then you have unstable. Or we can say unstable if K is less than a quantity Kc, which is rho G by gamma. Okay. So we can come up with a dimensionless variable called the Biot number from this calculation. Bond number from this calculation. But I will skip that for this moment. It means that if waves are if K is smaller than a certain wavelength, or if the wavelength, if lambda on the other hand, if the wavelength is larger than gamma by rho G, if waves are larger than a certain wavelength, gravity will basically contribute to the film becoming unstable, provided we have this inverse configuration. So this is also called the Rayleigh-Taylor instability. Except that it's for a thin film, but the basic idea is the same. It's a heavy fluid or a light fluid which becomes unstable. Now we still have the final general case of a thin film where we have all the forces, van der Waals, gravity and viscous forces. And we also want to look at the effect of the container, because in general thin films are not infinitely horizontal. The horizontal extent is not infinitely large. There is a finite container which can basically limit the range of wavelengths that are possible, because you cannot have a wavelength which is larger than the size of the container. And in such cases, we can basically come up with a stability criteria in terms of the size of the container. So we will do this in a short lecture after this. So with this, I'll stop the discussion on this. So let me quickly summarize what we have done so far in this lecture. We have started by looking at the evolution equation for the thin film. We've introduced the Wonderwall force in the form of a disjoining pressure. And then we have we made the expression compact by defining three parameters: G bar, C bar, and A bar. These are the gravity parameter, capillary number, and capillarity parameter, and finally the Hamaker constant or non-dimensional Hamaker constant. Then we derived a nonlinear partial differential equation for the height. We linearized it by saying that the perturbations are small relative to the mean value. And having done this, we basically got a linear partial differential equation. This linear partial differential equation, we carried out a stability analysis of this linear partial differential equation and looked at various special cases. We've also briefly touched upon the so-called Rayleigh-Taylor instability, where you have a heavy fluid sitting over a lighter fluid. We will look at the general case of all the forces: gravity, surface tension, viscous forces, and van der Waals forces present. We look at that general case in the next lecture. Thank you.